Swayam Prabha. Digital India. Educated India.
So in this lecture, we will talk about connections in ductile frames. We require ductile frames, especially in seismic conditions. When we design a structure for seismic loading conditions, the seismic loads are typically so high and they exert such a large force demands on the structures that it is unreasonable to design them for elastic behavior. Because if we want to behave a structure elastically under the most severe earthquake that it can expect in its life, then most likely the structure will become so heavy, so bulky, that it will be unusable. So for typical structures, we do accept some level of damage, but the idea behind the ductile designing of a structure is so that it can accommodate the damage without creating an overall instability in the structure. So structure should remain stable, structure should help prevent a life loss, and also be able to resist the load from the earthquake. So that is the typical philosophy. There are three different levels of analysis design methodologies that can be employed. So the one that is most commonly used by structural designers for everyday structure, including high-rise structures too, is the one that is known as capacity design using linear analysis. So this is also sometimes referred to as the response spectrum based analysis or response spectrum based design. Okay. So this is the most commonly used approach, and the idea here is that even though we expect the system to behave non-linearly, we expect the structural system to form hinges, we design the components, individual components, only up to elastic limit, and then we use some kind of scaling factors to calculate the actual performance of the structure. So in this approach, the advantages are that this is a simpler approach. It does not require so much of computational power because of the analysis is all linear, and we do not need very accurate constitutive relationships and connection behavior, etc. Whatever models that are easily available for connections can be utilized because the analysis in general remains elastic. The disadvantages of these methods of linear analysis based on capacity design based on linear analysis, the disadvantages of this method are that it cannot, first of all, predict the exact behavior. So we do not know exactly which member or which part of the structure is likely to fail first. Also, we have no idea about the expected behavior of the structure in an earthquake. We try to make sure that the structure remains safe, but that is all that the information we have. We cannot modulate the design based on a particular type of earthquake. So there was a design philosophy which is known as performance-based design, wherein the idea is that the structure should be designed to perform in a certain way under a certain magnitude earthquake. That kind of objective cannot be fulfilled with this approach. The approach that can be utilized to fulfill the objective of a performance-based design would require some level of nonlinear analysis. So the commonly used method in object-oriented or performance-based design approach is known as the nonlinear pushover type of analysis. In this analysis, we do not do analysis only up to the linear range. We understand that the structure is going to plastic range. We have to model the portions of the structure which are likely to undergo plasticization to as much accuracy as we can, and that's where the role of our models, the empirical models that we adapt for, so let's say for a column, if it's going to form a hinge, or if it is going to form a hinge in a beam, we would require the m-phi, moment curvature relationship for that hinge, or moment rotation relationship for that hinge. If our moment relationship is not accurate, then our model prediction will not be accurate. This approach could be utilized to assess the overall performance of the structure for a given earthquake. So typically you might have heard of the terminology like life expectancy, the life safety, the immediate occupancy, and so on, performance objectives. So such kind of design philosophy can be employed or can be met using this method. The third and the most complex one is the one that is known as nonlinear dynamic analysis. So in the second one, even though we were accounting for the plasticization of the structure, we were not really accurately accounting for the nonlinear, the dynamic aspect, the time variable aspect of the earthquake. So in a pushover analysis, we keep pushing in one direction in monotonic way, which tends to simulate the most severe earthquake, but does not really simulate the earthquake properly. In a nonlinear dynamic analysis, we actually take into account the inertial aspects of the building and also the time variability of the forces. And as a result, this is the most accurate method to predict the performance of the structure. And based on this, we can actually design individual components. But the challenge here is that having the exact information about the earthquake loading and also about the constitutive relationship of different components of the structure is very challenging, and if we make a mistake there, the results could be very misleading. Okay. So typically for most of the design projects, engineers, especially in India so far, mostly employ this technique, which is known as linear analysis based on capacity design. So in this course, we will focus our attention only on this linear analysis based design. And for this design to understand, first we have to understand a few terminologies. One of those is the distinction between DCE members in a structure and FCE members in a structure. So whenever we have a structural system which is supposed to resist the lateral loads, not every frame in a steel structure resists the lateral loads. Some frames resist and some frames are considered as leaning frames. They do not resist the lateral loads, they only resist the gravity loads. So we are going to talk only about the frames which are designed to resist the lateral load. So there could be an example such as moment resisting frame or a concentrically braced frame. This is an example of a concentrically braced frame where these braces are meeting the beam concentrically. There is also an alternative type of base frame which is known as eccentrically braced frame, which looks like this. And the undeformed configuration, these broken lines show the undeformed configuration. So these two bases do not meet at the same point to the beam. They meet with some offset, and that offset creates an eccentricity which actually creates a shear link. So in different systems, there are different components which are expected to undergo plasticization. Okay, and those components which are expected to undergo plasticization would be classified as ductility control elements, and they are the ones who would control the overall ductile behavior of the frame. So these components should exhibit a very significant amount of plasticity, a very significant amount of ductility. They should not break very easily. They should continue to deform, offering resistance for a very large extent. So in a moment resisting frame, for example, the beam ends not inside the column, outside the column, but ends of the beam. These are the locations which are considered to behave as a hinge, but with a significant amount of moment resistance, and they should form a hinge which will absorb most of the, or dissipate most of the energy from the earthquake. In a concentrically braced frames, typically braces are expected to behave that way. So braces are expected to plasticize and absorb that energy. Okay. In an eccentrically braced frame, the braces and the beams and the column are supposed to remain linear. They are not supposed to plasticize. It is the shear link, it is the portion of the beam which is loaded eccentrically that is expected to plasticize and absorb most of the, or dissipate most of the energy that is coming into the system. So these components which are supposed to behave, take plastic deformations, they are known as ductility controlled elements. So they are listed here. And then there is another set of elements which are surrounding elements which apply those loads to the DCEs. They are known as FCEs, force controlled elements. And the idea here is that we should design the DCEs for the expected deformation demand, and we should design the FCEs for the expected force demand. So this is the major classification, major distinction between two different types of elements in a lateral load resisting system that we should identify, and then we should go about with designing. For example, in a moment resisting frame, we cannot make a column as a DCE, because if the column forms a hinge, that can lead to a significant destabilization of the system. So we usually don't prefer the column to develop a hinge. Therefore, the DCE would be the beam ends and FCE would be the column and the column beam joint. There are a few more terms that I think it is important that I explain in the beginning, so that we understand the design methodology in detail. So here I am trying to emphasize the difference in the dynamic behavior of a linear system as compared to a non-linear system. So basically we took a pendulum. The pendulum had a natural frequency of 1 Hertz, that is the natural time period was 1 second. It was single degree of freedom system. It was subjected to an al centro type of earthquake loading. This is basically a time history, acceleration time history, which is typically used quite commonly. The system was assumed to have a 2% internal damping, and this type of linear system was subjected to the al centro earthquake. This was a specific time history of acceleration at the base, and then the response at the top, the displacement response at the top was observed. So this is the displacement response, which is relative displacement with respect to time. So we can see that maximum displacement or maximum drift with respect to the base is calculated as something like almost 4.5 to 5 inches. Then we change this system in such a way so that it does not remain elastic. That is, its natural time period is 1 second in the elastic zone, in the elastic range, but after a displacement of 1 inch, which is marked here as delta y, after it reaches a displacement of 1 inch, then it becomes a perfectly plastic system. That means it has zero stiffness at that time. And then again the same system is subjected to earthquake loading, al centro earthquake loading, and again the displacement at the top is measured. So one thing obviously we can see is that in the linear system we were getting a net zero displacement at the end, because system was coming back to zero position after the earthquake loading was completed. In a plastic system, however, there is a residual displacement. So after the earthquake is complete, the earthquake history has completed, there is a leftover displacement in the system, which is expected because the system has a plastic deformation, which is a permanent deformation. But here in this system, you might also realize that the total deformation, maximum displacement that we see is almost of the order of 4.5 to 5 inches, which is not very different from what we were getting in the elastic case. So in the first case, in the elastic case, the system was only moving on this straight line. In the second case, the system was moving on this line, on this blue line. Okay, and after the earthquake is completed, you might see that there is a small increase in the total deformation or maximum deformation in the system. But what is more noteworthy is that the maximum force demand is much smaller in comparison to an elastic system. So in an elastic system, the maximum force demand would have been almost equal to CE, because that was the maximum, because the system was always traveling on this path, on that diagonal line. But in a plastic system or elastic plastic system, the maximum force is limited by Cy. That is the point, that is the maximum force this system can resist when the yielding happens and the system plasticizes. Okay. So we can understand that there is a small change with respect to the original elastic analysis because of the presence of ductility in the system. In addition to that, also there is the effect of redundancy in the system. Because of that, there might be a small change in the deflection, but there is a very significant reduction in the maximum force demand. So how do we handle this change in response, in the maximum force response in the design provisions? If you go to IS 1893 part 1, you would see that there is a response spectrum, design response spectrum given in the code, which looks somewhat like this, and then the expression for the seismic coefficient, which is basically an acceleration term, that includes a few terms here. I'm not going to go into their detail, but there is a R value in the denominator, and this R depends on the ductility of the system. So if the system has a more ductility, the R value would be larger. And essentially what it says is that if you have a very large R value, you reduce or you scale this spectrum value with this R value, and then you get a new response spectrum. And you use this response spectrum for your design applications, which basically accounts for this reduction in response. Now, obviously, if my system is more ductile, so for example, if my system can accommodate much greater levels of plastic deformations before it fails, that means my system can go all the way up to here. In such a scenario, in such a scenario, we would have, or we can utilize a response reduction of up to this level. Whereas if the system is not very ductile, and maximum we can utilize up to this much of yielding or this much of permanent deformation, my response reduction would be only this much. So this factor with respect to this force, the elastic force that we would calculate here, or this factor with respect to the elastic force that we would calculate here, so this response R factor would be very large in comparison to this R, and that is definitely a function of how much ductility is available in the system. So in this slide, we have listed the values of response reduction factors for some of the steel structures. So in the first row C and row D, you can see there are ordinary moment resisting frames, and SMRF is a special moment resisting frame. Both of them are moment resisting frames. We have discussed how moment resisting frame works. So for them, the response reduction factor is taken as 3 and 5 respectively. And in case of braced frames, this is a braced frame with concentric braces, and this is for braced frame with eccentric braces. The response reduction factors are 4.5 and 5 respectively. So these are the typical magnitudes of response reduction factors. The systems that are not meant to be very ductile, the response reduction factor could be less than 3 also. Another factor of interest would be the deflection amplification factor, which is also associated with the same process. So as we have discussed, for the linear system, if the system were to behave linearly and the full load was applied on the system, the actual response would have been up to this point A, and the corresponding force demand would have been CE, and the corresponding displacement demand would have been delta E. However, a linear elastic plastic system behaves in such a way, and we find that the maximum force demand is only CY and maximum displacement demand could be delta U. Now comes the question of how do we map these into this analysis. So what we do actually is that we do analysis only for this much of load, only up to point B, and we do a linear analysis. And for that, what we do is actually we do linear analysis, then we scale it down in such a way so that we get the response for this point B. Okay, so that way we get the force demand measured somewhat accurately. Instead of CE, we measure the actual force demand for the elastic plastic system. However, when we do the linear analysis up to point B, what we actually get is the displacement demand of only delta Y, which is absolutely incorrect, because the actual displacement is likely to be delta U and not delta Y. Okay. So if we amplify it back again with the R factor, the displacement, we will get delta E, which may or may not be accurate, or which may or may not be exactly same as delta U. So there is a factor called CD, which can be used to amplify the displacements again to get an accurate estimate of the actual deflections. Right? So that factor is called CD. So for every given system, let's say we are talking about moment resisting frame of a special level of ductility, then for such type of a frame, there will be a particular R value given to us, which will correspond to this reduction from CE to CY, and there will be a particular CD value given to us, which would correspond to the amplification of deflections when we move from delta Y to delta U, which is actually the real deflections. So we can calculate the deflections using this method. There is another factor known as the overstrength factor. Overstrength factor is critical for the design of the components which are meant to be force critical, or which are meant to be force demand driven. Right? So you remember there were two types of systems. One was the DCE type of a system, and the other one was the force FCE type of system. So the overstrength factor becomes critical for the members which are FCE type. So basically FCE members were not supposed to plasticize or not supposed to undergo plastic deformations during the earthquake loading. So all the plasticization has to happen in the DCE type of systems. So how do we ensure that the members which are not supposed to plasticize do not plasticize, while the elements which are DCE are plasticizing? For that, we have to account for a couple of factors. One is that the first plasticization starts, and then the stiffness of the system starts to decrease, and then the system reaches its maximum value of, or maximum force resistance. This is the behavior of an FCE system. So the DCE system, which is transferring the same force to the FCE, this is the response of the DCE system, and the FCE system, which is elastic system, that is transferring the force to the DCE component, should not plasticize anywhere from here to here. So we do the basic analysis, elastic analysis, to get the demands up to this point. And then in the previous example, we had assumed that the response is like this, like a straight line. But that was okay for a linearly elastic, perfectly plastic type of a model. But most of the structural systems have quite a bit of strain hardening. This strain hardening could be the material level strain hardening. It could be because of the M-Phi curve, even for elastic plastic material properties. The moment curvature curve itself has some level of gradual increase in the moment until the entire cross-section plasticizes. Plus, in a structure itself, not all components will plasticize at once. So some components will plasticize, but some other components in the same structure which are supposed to plasticize would plasticize after some time, right? And therefore, the force demand in the FCE system may keep increasing. So, in addition to that, there is also one more factor, which is because of the difference in the characteristic strength of the material versus the expected strength of the material. So, for example, if there is a DCE system, a hinge which is supposed to form, and we know that it forms at 250 MPa strength because that is the strength given for the material, but it may so happen that that material, instead of 250, has a yield strength of 270, expected yield strength of 270 MPa. So, characteristic strength might still be 250, but if that is the case, we have to be careful that if this member is going to plasticize, it is going to take or absorb a lot more force or a lot more movement before it plasticizes, which means that the neighboring members which are transferring that force but they are not supposed to plasticize should be able to remain elastic for a much greater force. So all those factors that I just mentioned are taken care of by this component or this factor which is known as the overstrength factor. So overstrength factor, so basically we do our analysis, we get this demand, linear elastic demand, we design our components, but then our DCE components, but for FCE components we have to again amplify the demand so that we can calculate the force demand, which would account for all this reserved strength in the member which is available after the first yield happens in the structure. So here I am summarizing the design approach in a few steps. So basically the idea is, first we have to do two-step designing. One is the strength limit state and the other one is serviceability limit state for earthquakes. So in the strength limit state for earthquakes, we basically use the response reduction factor and we do the modal analysis, or we can calculate the time period, and then we can use the response spectrum to calculate the earthquake force demand. For that earthquake force demand, we use one of these three combinations, if you can see closely. First combination is dead load 1.2 times, live load 1.2 times, and earthquake load 1.2 times. These are given in IS 800. And the other combination is 1.5 times the dead load and 1.5 times the earthquake load. This time we don't take any live load. And another combination would be when we reduce the amount of dead load from 1. It is 0.9 dead load plus 1.5 earthquake load. So for these loads, we do a linear analysis. Here in the earthquake load, we have already reduced the earthquake load for the response reduction factor, accounting for the ductility of the system. Now, whatever force demands we get in the components which are supposed to be DCEs, we design them for this much of force demand. Subsequently, we have to make sure that these components behave in a ductile fashion which is commensurate with the response reduction factor we have taken. Therefore, that can be ensured by appropriate detailing. So, for example, if it's a beam end, then it should be able to develop sufficient plastic hinge, meaning that it should be able to have sufficient rotational capacity before it starts to lose its flexural strength. So, for that, certain compactness ratios are required in the cross section that we have to meet. So, such kind of detailing requirements have to be satisfied. Once we do that, then we start designing other components. So DCE can be designed for the reduced forces and by making sure that there is enough ductility available. Subsequently, we will go for designing of the FCEs, which are force driven members. For their design, we use different set of load cases. These load cases are given in clause number 12.2.3 of IS 800, which are different from the ones that are given in general cases on table 4. So in these cases, you might see that the earthquake loading has been amplified, and this amplification is nothing but the omega factor, the overstrength factor, which basically accounts for all the different types of reserved strengths in the structure, after the first yielding of one of the DCEs. And then the FCEs are designed for this load. I'm sorry, this is incorrect. This should read as FCE. So DCE are designed for this load and FCEs are designed for these loads. So that's how the strength limit state can be satisfied. Now when it comes to serviceability limit state, the load combinations that are given in IS 800 for serviceability limit state are these. So one load combination includes dead load plus 0.8 live load plus 0.8 earthquake load. The other load combination that is given is 1 dead load plus 1.0 earthquake load. So for both of these, we calculate the demand in the displacement demand in the structure by doing a linear analysis. Here, the earthquake load again is the one that is reduced for the response reduction. So this is because of the response reduction. This is the analysis. Subsequent to that, whatever displacements we get in the system, we amplify those displacements by a factor of CD, which basically accounts for this the amount of ductility that is available in the system. We account for that by using this factor CD, and then we calculate new deflections. So these deflections are greater than the deflections that we had calculated from the analysis. Then we make sure that our drift limits are satisfied. Okay. However, this particular part is not exactly done the same way as per the current Indian Standard Code IS 800. The CD factor is not explicitly mentioned, and I will talk about that in a minute. So as we had just discussed, the force demand in FCEs has to be calculated by amplifying the earthquake force by a factor of overstrength factor. So the American Standard Code gives you explicit values of overstrength factor, omega 0. These omega 0 values are different for different types of structural systems. We will talk about the values in a minute. So those respective omega naught values have to be used. In the Indian code, however, the overstrength factor in IS 800, the overstrength factor is not mentioned explicitly. It is present in the form of this factor 2.5, which is a constant value, and for all different types of structural systems, the same value needs to be utilized. There is another approach to calculate the force demand on the FCEs. So, for example, if we are designing a column in a moment resisting frame, the column would be an FCE member. Now, one way to do that is to take this lump sum value of 2.5 and assume that there is an overstrength of 2.5 available, and whatever force demand we get in the beam, amplify that with a factor of 2.5, and that would be the force demand on the column. However, the other approach could be to actually look closely into this system and see how much actual, when this beam is plasticizing, it would plasticize at exactly this much of moment, and these are the different forces acting on the member, and we can go into the detail and try to find out how much force it would be resisting when this plasticization is happening. And in that process, we need to account for all the different types of strain hardening and other yielding points and everything. So this type of analysis can also be done, but this is more cumbersome, and usually it is not done as frequently. Sometimes some empirical equations are available. Those equations could be used instead of these factors, but typically people use these factors directly. The three coefficients that we just talked about, the response reduction factor, the overstrength factor, and the deflection amplification factor, their values I have taken here in this table. I have listed their values from the different codes. So here I have taken the values given in the American Society of Civil Engineers ASCE 7 document, and also here I have listed the values of R as per IS 800 for different types of structural systems. These are for moment resisting frames, and these are for braced frame systems. And you can see that there is quite a bit of variability. The American code is more ambitious in a way, or less conservative in a way, so that they use a response reduction factor of almost 8. So that is basically they have a lot of confidence in the ductile behavior of SMRF systems or SBF systems, and they use a very large response reduction factor. In the Indian code, we are a bit more conservative, and we don't reduce the demand by such a large magnitude. We reduce it by a factor of 5 at max. As I had mentioned before, the Indian code does not explicitly mention the overstrength factor anywhere, but it gives a constant value of 2.5 for all different types of frame systems. The American code gives a overstrength factor of 3 for moment resisting frame and an overstrength factor of 2 for the braced frames. The displacement amplification factor we will talk about in a minute. Also, one might know that there are different codes in India. They don't necessarily reconcile with each other. So the response reduction factor that is given in IS 800 for an ordinary moment resisting frame, and what is the meaning of ordinary, we will talk about in a few minutes. In ordinary moment resisting frame, the response reduction factor as per IS 800 is 4.0, whereas for the same system, IS 1893 part 1, which controls the design force, the earthquake force demand calculations, prescribes a value of 3.0. So there is a bit of discrepancy between different codes, and it could be anybody's guess to follow one of the two codes. So as we have mentioned before, the IS 800 does not explicitly mention over strength factor and the deflection amplification factor. However, it does mention the response reduction factor R. So this omega 0 and CD factors are missing in the IS 800. However, they are implicitly incorporated, which we have seen some glimpses of it. There is also another document which is known as draft CED 39 18640, which is basically an equivalent of IS 13920, which would give the prescriptions for ductile detailing of steel structures for earthquake applications. So this document does explicitly mention the overstrength factor, right? So the values in this document are slightly different from the values that are mentioned in IS 800, and if this document would come into force, I believe that should supersede the values mentioned in IS 800. Okay. So, but IS 800 does not mention the overstrength factor, but as we had seen before, it uses some load combinations for the design of FCE type of components, and those amplification factors are basically nothing but, the load factors are nothing but the overstrength factors. For the limit state of serviceability, since I had mentioned that CD value is actually used to amplify the deflections. So first we calculate the deflections using elastic analysis for the reduced response, including the response reduction factor. Then we amplify the deflections by the CD factor. But the Indian code IS 800 does not explicitly mention the CD factor. So then how does it deal with the change in amplification? What it does is that it actually sets a very low limit on the drift values, which in a way is same as saying that if the CD factor is applied, then the deflections limit would be slightly higher. So if I go to IS 1893 part 1, clause number 7.11.1, it mentions that the story drift limit is set as 0.4% of the story height, okay, which is relatively small in comparison to, if we compare it with ASCE 7, that is American code, it says that the story drift limit would be between 2% and 1%, depending on the occupancy level. So in ASCE 7, you are required to first calculate the deflections under the elastic analysis, which is under the reduced response. Then you amplify the deflections with this CD factor, multiply all the deflections with this CD factor. That will give you the final deflections or real deflections. Those real deflections should be within 2% to 1% of the story height. The Indian code, it does not apply that amplification factor, deflection amplification factor. Whatever we got from the analysis, it simply says that that value should be only 0.4% of the story height. So it may appear to be more stringent, but it is not. It is basically the ratio between 2% and 0.4% could be designated as the deflection amplification factor. The only difference between this code, the Indian code, and the ASCE 7 is that ASCE 7 gives different values of CD for different types of framing systems, whereas the Indian code gives a constant value because it gives it sets a single lower limit for deflections. Now here, one thing we must be careful about is that these provisions are taken from IS 1893. IS 800 gives different load combinations for the serviceability limit. So IS 1893 says that this 0.4% should be done while considering a load case where the partial load factor applied to the earthquake load is 1.0. Okay. So we can interpret that that statement as if we should take the load combination, which is 1.0 times dead load and 1.0 times earthquake load. However, there is another load case which is 1.0 times dead load plus 0.8 times live load plus 0.8 times the earthquake load, which is mentioned in IS 800. And for that, what should be the deflection limit? That is not mentioned. So to go by intuition or to go by general logic, we can say that for both these combinations, let's check for the deflection limit of 0.4%. Typical load resisting systems we had discussed very early in this lecture. One type of system is the moment resisting frame system, and the other one is a braced frame system. Now the two systems are inherently different. In most of the steel structures, we usually have only a few of the frames designated to resist the lateral loads. Rest of the frames are typically designed only to carry the gravity loads, and they deflect as the lateral load resisting system deflects. So in a typical frame, only a few of the frames are designed to resist the lateral loads. The rest of the frames are considered as leaning frames, and they only resist the gravity loads, and they lean or they deflect as the lateral load resisting system, lateral load resisting frames deflect. So in a moment resisting frame system, the connections between the beam and the column are made rigid so that it has a lateral load resisting capacity. In a braced frame system, however, we don't make rigid connections between the beams and the columns, but we provide concentric braces like the ones that are shown here, and there are different varieties of such frames, such braces which can be provided. One we had seen before, it was basically a chevron kind of a brace, where the brace was meeting in the middle of the beam. The two braces were meeting in the middle of the beam. There can be another variety wherein you may have a single brace on each side and two bays may be covered. This is kind of a X bracing. For most of the lateral load resisting applications, we avoid any K type of a bracing wherein the braces meet the middle of the column. It is okay to meet at the middle of the beam because beam is not such a critical member for the overall stability of the structure, but having braces meeting at the middle of the column is strictly prohibited under earthquake loading conditions. So braced frame systems, whatever they are, because of their diagonal members, they act as truss members and they increase the lateral load resistance capacity very significantly because they have very large axial stiffness. So these systems typically behave in a much more stiff manner as compared to moment resisting frame systems, because moment resisting frame systems rely on the flexural stiffness of the beams also, and if we want to increase the flexural stiffness of the beam beyond a certain limit, we end up using very deep beams that may become uneconomical. So sometimes therefore, typically, MRF systems or moment resisting frame systems are relatively flexible. The one good thing about moment resisting frame systems is that they don't have any members blocking these openings, and therefore you have a complete freedom. The designer has a complete freedom to provide windows and doors wherever they want. But in braced frame systems, it becomes an hindrance, because if we want to provide a door here because of the braces that are passing through at this cross section, providing a door or a window here may be very difficult or may not be possible.